Dear students, in this part, let us discuss refraction through spherical refracting surface when object lies in denser medium. That is case number 2. So first we have to see this ray diagram. Here XPY represents a convex spherical refracting surface and R represents radius of curvature, that is the distance of center of curvature from the pole, and mu2 represents absolute refractive index of the material of the spherical refracting surface, and this spherical refracting surface XPY is kept in a rarer medium having absolute refractive index mu1. So let a point object O is placed on the principal axis inside the denser medium at a distance u from the pole. So let us consider a ray of light OA emerging from this point object and incident on XPY, making an angle of incidence I. And here CN, the straight line CN represents normal line, and it should be always passing through the center of curvature C. So here light is traveling from denser medium to rarer medium. So after refraction, the refracted light ray bends away from the normal and meets the principal axis at capital I. So here I represents the position of the real image formed by this spherical refracting surface XPY, and here small r represents angle of refraction. And again, let us draw AM perpendicular to the principal axis such that M should be very close to the pole, that is point P, and alpha, beta and gamma represent angles formed by the incident light ray, the refracted light ray and the normal line with the principal axis. And here B represents image distance, the distance of image capital I from the pole, and U represents the object distance, that is the distance of object from the pole. Now the figure is the XPY na convex spherical refracting surface laire, aduga O na position of the object, point object, and object dagi light ray ama koina lahal asi OAJ aduga XPY di yairaba, making angle of incidence I. On the light se denser medium to rarer medium satpanina refracted light rays normal dagi phaidorani aduga principal axis ka I da unare meet tawre, aduna I jina sigi point object sigi real image udiba, adu R jina angle of refraction oire, adu akoina AM haiba line je principal axis ta drop tawre, perpendicularly drop tawre, tawudabu point M ka point P ka yamna close oigani. Aduga alpha, beta and gamma jina kainoabu angles formed by the incident light ray, refracted light ray and the normal with the principal axis. So we have to find out the relation between mu2, mu1, U object distance, V image distance and radius of curvature capital R. So we may write like this: let XPY be a convex spherical refracting surface whose absolute refractive index is mu2 and having radius of curvature R, kept in a rarer medium of absolute refractive index mu1. A point object O is placed on the principal axis inside the denser medium at a distance u from the pole. A ray of light OA emerging from the point object is incident on XPY making an angle of incidence I. Since light is traveling from denser to rarer medium, the refracted light ray bends away from the Norman Cn and meets the principal axis at I, capital I, at a distance v from the pole. Hence, capital I represents the position of real image of the object O. Then, AM is drawn perpendicular to the principal axis such that M is very close to the point P, that is pole. Alpha, beta and gamma be the angles formed by incident light ray OA, refracted light ray AI, and the Norman Cn with the principal axis respectively, as shown in figure. Next, we have to apply Snell's law in this case. So here, in this figure, light is traveling from denser medium to rarer medium, making an angle of incidence I and angle of refraction R. So, applying Snell's law, we may write like this: sine of angle of incidence, sine I divided by sine of angle of refraction, that is sine R, is equal to relative refractive index of rarer medium 1 with respect to denser medium 2, because light is traveling from denser medium to rarer medium 1. And this mu1 2 can also be expressed like this: absolute refractive index of rarer medium 1 mu1 divided by absolute refractive index of denser medium 2, that is mu2. So write in equation number 1. So in equation number 1, sine I by sine R equal to absolute refractive index of rarer medium mu1 divided by absolute refractive index of denser medium mu2. Next, let us assume that I, R, alpha, beta and gamma, that is angle of incidence, angle of refraction, alpha, beta and gamma are small angles. Then sine I can be written as small I and sine R can also be written as small r. That is, when angles are very small, then we can neglect sine function. So we may write like this: sine I is approximately equal to angle I, and similarly sine R is also approximately equal to angle R. So equation number 1 becomes I by R. That is, instead of sine I and sine R, simply we may write angle I and angle R. So I by R equal to mu1 by mu2. So from this, I into mu2 equal to R into mu1, and write in equation number 2. Then we have to try to express angle I and R in terms of alpha, beta and gamma. So we have to consider this figure. So let us take a triangle containing angle of incidence I. So we have to take this triangle AOC. So in this triangle AOC, gamma represents an exterior angle of this triangle AOC, and I and alpha represent two interior opposite angles. So this exterior angle gamma is equal to the sum of these two interior opposite angles, that is I and alpha. So we may write like this: from triangle AOC, angle gamma equal to I plus alpha, and this would be equal to I equal to gamma minus alpha. So again we may write like this: instead of gamma, angle gamma and angle alpha, we may write tangent of gamma minus tangent of alpha, because these two angles alpha and gamma are also very small angles. So we may write tan alpha and tan gamma instead of alpha and gamma. Then angle I can be expressed like this: I equal to tan gamma. See, from this figure, let us take right triangle AMC. So tan gamma is equal to perpendicular divided by base, that is AM by MC, and similarly tan alpha. Then we have to consider right triangle AMO. Then again AM represents perpendicular and MO represents base. So tan alpha is equal to perpendicular by base, that is AM by MO. So write in equation number 3. Again from triangle AIC, that is we have to consider a triangle containing angle of refraction small r. So let us take triangle AIC. So in this triangle, R represents an exterior angle and angles beta and gamma represent two interior opposite angles. So this exterior angle small r is equal to the sum of two interior opposite angles, that is beta and gamma. So from this triangle AIC we may write like this: R equal to beta plus gamma. Then instead of beta and gamma we may write tangent of beta plus tangent of gamma, since beta and gamma are also very small angles. Then again let us try to express this tan gamma and tan beta in terms of, say, perpendicular, side and base. So let us take triangle, right triangle containing angle beta, and it should be right triangle AMI. So from this right triangle AMI, tan beta is equal to AM by MI, that is perpendicular by base. So we may write tan beta equal to AM by MI. And let us take another right triangle containing angle gamma. So it should be triangle AMC. So from this right triangle AMC, tan gamma equal to perpendicular AM divided by base, that is AMC. So we may write like this: tan gamma equal to AM by MC. So finally angle R equal to AM by MI plus AM by MC, and write in equation number 4. Then putting the values of angle of incidence I and angle of refraction R in equation 1 we have. So in equation number 1 we have written small I into mu2 equal to small r into mu1. So instead of I and R we may write like this: AM by MC minus AM by MO equal to mu2, and this represents I, and AM by MI plus AM by MC into mu1, and this represents R. So we may write like this. Then AM can cancel from both sides. Then instead of capital M we may it replaced by capital P, because M and P are very close to each other. So we, from this equation again we may write like this: mu2 divided by PC. Instead of MC we may write PC, and we have to open this first bracket. So mu2 by PC minus mu2 by PO equal to mu1 by PI plus mu1 by PC. AM cancel from both sides, and write in equation number 5. Now we have to use sign conventions. So PO, here PO represents object distance, that is distance of object from the pole. So the direction of measurement of object distance, that is from P to O, is against the direction of incident light ray, that is OA. So this U, object distance, should be negative. And similarly radius of curvature, that is the distance of center of curvature C from the pole. So direction of measurement of radius of curvature, that is from P to C, is also opposite to the direction of incident light ray OA. So the value of capital R should be negative. So here we may write PC equal to minus R. And again PI, here PI represents image distance, distance of image from the pole. The direction of measurement of image distance, that is from P to I, is along the direction of incident light ray, that is from right side to left side. So B should be positive. So we may write PI equal to plus B. So we have to put the values of PO, PC and PI in equation number 5. We have already derived. So from equation 5 becomes mu2 divided by minus r. Instead of PC, you have to put minus r, minus mu2 by minus u. Instead of PO, we have to put minus u, and this will be equal to mu1 by v. That is, instead of PI, we have to put plus b, plus mu1 by minus r. That is, instead of PC, we have to put minus r. So from this equation, we may write mu2 by minus r, minus minus plus, so mu2 by u equal to mu1 by v, and plus minus t minus, then we may write mu1 by r. Again, you have to bring this mu2 by minus r in the left side to the right side, then it will become positive. So then again, this mu1 by v in the right side is bringing to the left side, then mu1 by v becomes negative. So we may write like this, mu2 by u minus mu1 by v. So from this equation, we may write like this, mu2 by u minus mu1 by v equal to mu2 by r minus mu1 by r. Then capital R in the right side can also be written like this. That is, taking LCM, then we may write like this. So mu2 by u minus mu1 by v equal to mu2 minus mu1 divided by r, and write it equation number 6. So this equation 6 represents the relation between object distance u, image distance v, radius of curvature capital R, absolute refractive index of rearranged medium mu1, and absolute refractive index of denser medium mu2 when an object lies in denser medium. And in case of object lies in rearranged medium, last time we have derived, and the equation should be like this, mu2 by b minus mu1 by u. But in this case, mu and u, object distance and image distance v, are interchanged. So in this equation number 6, mu2 by u minus mu1 by v equal to mu2 minus mu1 by r represents relation between u, v, r, mu1, mu2 when object lies in denser medium.